Dr. B here. So this is topic 5.3, concentration changes over time. One of the objective for this topic is to be able to identify the rate law expression of a chemical reaction using data that shows how the concentration of reaction changes over time. So there are the three different types of orders listed, the 0, first, and second, and they each have specific equations that need to be known. So you'll notice that to solve for them, so to speak, or to be able to recognize what type of order reaction, you'll notice that the 0, first, and second have specific things that are different for each that will help you be able to recognize those particular things. I know I'm kind of saying it kind of weird, but you have to be able to recognize the type of order reaction based on the equation given, because that will be listed on your in your sheets, but they won't tell you what type of order it is, so you have to know that. It also lists the equation for half-life that we're going to be talking about too. So the order of reaction can be inferred by the graph of concentration of reactant versus time. So if a reaction is 0 order with respect to a reactant being monitored, the plot will be linear, but it's just the reaction concentration, the actual concentration itself versus time. If it's a first order, the natural log will be plotted and it will be linear. If it's a second order, it's going to be the reciprocal of the concentration. So 1 over the concentration. This is the natural log of the concentration, and this is just the concentration. And those are the ones that are going to be linear. Oops, I missed that one. Linear and linear. So being able to recognize what is linear, that's going to be the key, to be able to know what type of reaction just based on the graph. So here are the equations that you're going to be given. The slopes will be the slopes of the concentration versus time data for 0th, first, and second. They can be used to determine the rate constant of the reaction. So you'll notice there, all those are there. It's listed in the order 0th, first, and second. So those are the ones you're going to have to be able to recognize for this particular topic. So 0th order reaction, the rate equals a K constant times the concentration of A to the 0. Basically, it'll be rate equals K. So the slope K, the slope of the concentration for K will be the negative slope. So whenever you see it on the y-axis, it's going to be the just straight up concentration, the reactant in the brackets on the y-axis, and the time will be the x-axis, and it's going to be a negative slope, and it's linear. That means it's 0. If it's first order, rate equals Ka to the first, K times A, concentration of A to the first. So K will be negative slope, but the y-axis is the natural log of A. That's what you need to be able to know. You have to know it's a negative slope and the natural log is linear. If it's second order, it's the inverse of your concentration of your reactants, and that's a positive slope that will be linear. So these slides that I just showed you all, those are the ones that are going to be important for you to recognize. And like I said, those are going to be easy points if you're able to get those. Free response question. So nitrogen dioxide is produced as a byproduct of the combustion, blah, 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 blah. Sorry. So you have nitrogen dioxide decomposes to produce nitrogen monoxide and O2, oxygen gas. The concentration of a sample of NO2 is monitored as it decomposes and is recorded on the graph below. The two graphs that follow it are derived from the original data. So you see your three graphs there. Letter A, explain how the graph indicates the reaction is second order. Write the rate law for the decomposition of NO2 based on your answer in A. This looks like it could be your FRQ, right? So it tells you that it's second order. How do you know it is second order? So we have a concentration of NO2 for the y-axis. We have inverse in the natural log. So it tells us that the reaction is second. It tells us that the reaction is second order. So how do we know that? Well, if you look at these, you see that we have NO, the inverse of NO over NO2, I'm sorry. This one right here, this is the one that's pretty linear compared to the other ones. So the reason why we know that this is a second order reaction is because the inverse of the reactant is a linear graph. So a linear graph in the inverse tells us that it's second order. Write the rate law for the decomposition of NO2. So we know that it's second order and there's only one reactant. So it's going to be rate equals K times the concentration of NO2 squared. Decomposition of hydrogen peroxide is represented above. A student monitored decomposition of 1 liter of H2O2 at a constant temperature of 300 Kelvin, recorded the concentration as a function of time. The results are given below. Which of the following statements is a correct interpretation of the data regarding how the order of the reaction can be determined? So letter A, the reaction must be first order because there's only one reactant species. Letter B, the reaction is first order if the plot of natural log of H2O2 is a straight line. The reaction is first order if the plot of 1 over the H2O2 concentration versus time is a straight line. Reaction is second order because 2 is a coefficient of H2O2 in the chemical equation. So notice how, well, I'll give you all a second, but notice how it just gives you data, but like it doesn't want you to plot. Remember, these are 90-second questions at the most. So let's see if we can do process of elimination. The reaction must be first order because there's only one reactant species. That's not true. The reaction is first order if the plot of the natural log of the hydrogen peroxide concentration versus time is a straight line. Is that true? So if it's just a straight up concentration, it's a zero reaction. If it's a natural log, and it's linear, it just tells you it's a straight line. Then it's a first order, right? Letter B. That's the correct answer. Your response question. So blue fluid coloring can be oxidized by household bleach to form colorless products as shown above. A student used a spectrophotometer set at a wavelength of 635 to study the absorbance of the food coloring, blah, 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 blah. Based on the graphs above, what is the order of reaction with respect to the blue food coloring? So notice how it talks about spectrophotometry, like Beer's law and all that stuff. It tells us about it, but really the question here is not even related to it. All it wants you to know is what order is this reaction based on the data. Let's look at our graphs. So remember that absorbance and concentration are proportional in terms of Beer's law. So let's see, kind of blurry, but it's okay. Absorbance, natural log, and inverse. Notice how, remember when we're trying to pick the order reaction, it all has to be linear. The only one that's linear is the natural log. So what does that mean? It means that this order reaction is first order because that's the only one that's linear. See, these are kind of easy. We kind of want these problems, don't we? The order of reaction can be inferred from a graph of concentration. Well, we said this already, so this is a repeat. Moving on. Whenever we talk about half-life, it is related to first order kinetics. So whenever you see a question about half-life, think about first order. Not first order like Star Wars, not sponsored, but you know. So half-life is a critical parameter for the first order reaction because the half-life is constant and it's related to the equation provided. Radioactive decay processes provide an important blah, blah, blah. First order kinetics. Natural log, first order kinetics, linear line. So keep that in mind. You may see a question that's just going to say, half-life is shown here, blah, blah, what type of order reaction? First order right away, boom. Half-life, first order. Free response question. Determine the half-life of iodine 131 based on the plot provided. So how do you figure out the half-life? So we're looking here, and we can see that based on what they provide us, technically, we have 24 days, and it goes from 16,000 to 2,000. So what is the half-life? For my stuff here, for this problem here, we're starting off at 16,000, and we have to go until this is cut in half. So 16,000 goes down to 8,000. And basically, the half-life is how long it takes for half of that, whatever it is, to half be gone. So 16,000, half of that is 8,000. So we then go to our curve, go down here. My half-life for this is 8 days. There you go. The half-life is defined as the amount of time it takes, blah, 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 for the radioactive sample to decay to half its original amount, so half is 8 days. The data can be used to show that decay is a first-order reaction as shown here. Label the vertical axis of the graph above. So again, this is testing to see if you know what type of order reaction is focused on with these half-life questions. So we have to know that it is going to be first order. And if it's first order, your y-axis needs to be the natural log. And the concentration is the rate of decay. What are the units of reaction, or what are the units of the rate constant if this is a first order reaction? So it's going to be inverse days or 1 over days. Explain how the half-life of iodine 131 can be calculated using the slope of the line plotted on the graph. The slope of the line could be calculated, used to determine the rate constant, and then plugged into the half-life equation to solve for the half-life. Easy ways to determine half-life. If it tells you the half-life is 1,600 years, after 4,800 years, how many grams of a 0.25 gram sample is left? So you got to know your fractions for this. So if I have 0.25 grams of a sample, and I do a half-life here, this is going to be 0.125 grams. Well, first of all, how many half-lives are here? 3 half-lives. So my next half-life is going to be 0.0625 grams. Then one more half-life is going to be half of that, which is going to be 0.03125 grams. So think sig figs. This is going to be 0.031 grams, my sample. The half-life is 3 minutes. How long will it take for a 16-gram sample to decay to 1 gram? Interesting, huh? So, 16 grams, get all the way to 1 gram. So how many half-lives? My first half-life, 8 grams. Second half-life, 4 grams. Third half-life, 2 grams. So first, second, third, fourth would be 2 to 1. So this is going to be a total of 4 half-lives. So this is going to be 12 minutes. 3 times 4. What percent of a sample is left after 99 seconds, assuming the half-life of a sample is 33 seconds? So this is kind of crazy. It kind of sucks, actually. This question kind of sucks. It kind of confuses me too when I try to explain it, but we should be good. What percent of a sample? So the trick is to know what's the percent that's left over after so many samples. Sorry, after so many half-lives. So I'm going to write this down. So 100%, half of that is 50%, half of that is 25%, half of that is 12.5%, half of that is 6.25%, half of that is 3.125%, half of that is 1. Whatever, 5. So after 99 seconds, how much percent of this? We don't care the mass. All we care about is the percent. If the half-life is 33 seconds of a substance, and 99 seconds passes, that means that is a total of 3 half-lives. So 1, 2, 3. After the third half-life, what's the percent that's left? 12.5% is left over. So this is what I kind of used earlier, but it may ask you how much is left over. So the way that we can use this, kind of knowing our fractions and percentages, like 1/4 is 25%. 12.5% is 1/8, 1/16, 1/32, and then 1/64. So maybe you can use that, as well to help you figure out how much is left for these half-lives. That is it right now. If you have any questions, please let me know. Thanks, guys.